Welcome to the, I should probably go a slide back here. Welcome to the presentation of the first assignment of operating systems. So today we are going to talk about the first assignment mainly. And before we start, we probably also need some more background. Let me just briefly select the slides here and then we can start. Memory management in SWEP is one of the tasks in the first assignment, because you will have to implement some things like multi-threading, and that means that all the threads need their own stack and you have to place them somewhere in the memory. So you have to manage this memory. In the case of fork, for instance, you have to copy the memory from one process to another. Sound is strange, okay? Sound is kind of strange. Maybe let me check what the sound, whether there's any problem with the sound on my side. Interesting. Okay, let me hear that. Sounds funny. Okay. Okay. Is it better now? It shouldn't be the connection. Okay. There is an echo. The echo should be gone now. So I just had to enable the echo for a second so that I can actually also hear what is going on. But now it should be disabled again, and so the echo is also gone. Okay, let's continue. Memory management in SWEP. We are going to talk about processes and threads, and for that we need memory management for the stacks, for copying the address space of one process to a new one. When we implement exec, we also need to map pages into the new process, and those are all tasks that we need to implement and that all rely on virtual memory. So even though the first assignment is not entirely about virtual memory, the second assignment is a lot more about virtual memory. It still uses virtual memory all the way through. Let's talk about memory management in SWEP. So we are talking about a 64-bit system here, and 64-bit system, you will have not actually 64-bit of virtual address space, but the virtual address space is limited to currently 48 bits of virtual address space. So let me move this a bit like this. That means 48 bits of virtual address space, that we have an address space of 256 terabytes. 2 to the 8 is 256, and 2 to the 40 is a terabyte. 256 terabytes. The user space starts at address 0 at the null pointer basically, and it has a size of 128 terabytes. The kernel space, this is really nice because in 32-bit mode the kernel space starts at 2 gigabytes, and if you take a look at 2 gigabytes as a hex number, you will see that it's only this 8 and then all zeros. This is 2 gigabytes. In 32-bit mode, this is also minus 2 gigabytes because it's exactly half of the 4 gigabyte address space. Now what's nice about this is if you extend this to 64-bit, it's still at minus 2 gigabytes because you just sign extend this. So the kernel space is at minus 2 gigabytes and the size is 1 gigabyte. We also have an identity mapping. On Linux, we call it the direct physical map. In SWEP, we call it the identity mapping, which is at minus 16 terabytes and it has a size of 1 gigabyte. How does this identity mapping work? We take the first physical address and map it, or the first physical page at physical address 0, and map it to this address here in virtual memory. Virtual memory, this address here accesses the first page in the physical memory. address 0. If I increase this address, it will increase in the same way in the physical memory. So this just linearly maps directly the physical memory into our virtual address space so that we can access the physical memory. The identity mapping, yes, at minus 16 terabytes. Why is it there at minus 16 terabytes? Because I thought this is a nice address. I just chose this constant and thought, oh, it's nice. It's 5 Fs and then only zeros and a nice address. If you take a look at Linux, for instance, Linux also has an identity mapping, the direct physical map, but it has a much weirder address and therefore it's less convenient to work with. So the kernel space, so there's a question in the chat where the kernel space is exactly. So in case of 4 gigabytes, the kernel space is at 2 gigabytes and 4 gigabytes minus 2 gigabytes is exactly 2 gigabytes. So no matter whether you say it's 2 gigabytes or minus 2 gigabytes, you get to the same result. In 64-bit mode, we are talking about terabytes of memory. So in this case, the kernel space would be at 256 terabytes minus 2 gigabytes. So it's not 254 terabytes because terabytes and gigabytes is not the same. It's 256 terabytes minus 2 gigabytes. What was GIB versus GB again? Yeah, in general, I should write everywhere GIB for GB bytes. That's the power of 2 variant, and gigabytes is actually not the power of 2 variant. But we always in this course in this course we will always mean GB bytes, not the 10 to the something, but the 2 to the something variant. So it's always the binary base size. Let's talk about the address space. And we start here with this page map level 4. We will see this on the whiteboard in a second as well. Every process has a page map level 4. The kernel has its own page map level 4. This is the current status in SWAP already. And this maps virtual to physical addresses. When we perform a system call, we jump into the kernel, but the page map level 4 stays the same. So we can still work on the same address space. The identity mapping can be used, as I said, for physical access. And this means we are at the point where we need the whiteboard. Let me see, can I hide this slide for a second? Yes. Okay. So let's start again with the drawing here, and we do something that is similar to what we did yesterday. We start with our virtual address space. So the virtual address space is maybe here. Virtual address space. The virtual address space now is larger than yesterday because it goes from 0 to 2 to the 64. This is a lot, 2 to the 64. But actually, there's a large part in the middle that we cannot use. This part here, we call this the, I'm a bit too high here, non-canonical. This is the non-canonical area. In this non-canonical area, we cannot do anything there. This area cannot be mapped to physical addresses. It's just invalid virtual addresses. And if we try to access them, we get a general protection fault, which means that our process will crash. Let's see where these borders are. So this goes up to 2 to the 47. And this is 2 to the 64. So this number minus 2 to the 47. This is of course a bit, not so nice to write down. So let's write this also in a different way that it's more easy to remember. I will do that now. So we have here 0 to 128 terabyte. And here we start, we go up to 256 terabytes, but this is now 48 bits. And basically we just ignore this part in the middle. What is the purpose of having canonical space? Well, we want to have 64-bit pointers, but at the same time, we don't really have a use for that yet. The hardware doesn't actually support 64-bit pointers. But in the future, the hardware might support this space. So this is a future-proof design. We can increase the address space. We can decrease the size of the of this non-canonical space. And if we do that, then we have more virtual address space. But this gives us future compatibility. Okay. In the chat, there's a comment that something is 1 gigabyte large, starting at -2 gigabytes and growing downwards. There's nothing growing in the numbers that I've shown to you. These are fixed numbers, nothing grows there. Okay. Let's, so to make this very simple, we will just ignore this non-canonical area and draw this as a line in the middle. This is makes it a lot easier for us to work with that. So let me do that here. I will just draw this line here in the middle, and this is now our non-canonical area. The graphic, of course, is misleading because the non-canonical space would actually consume almost the entire address space. That's the largest part of the address space, the non-canonical part, for future compatibility. Okay, so 128 terabytes here. Okay. This is our virtual address space. We had the physical address space somewhere up here. Let's draw it maybe here. Okay, like this. This was the physical memory. And we had also this design that we wanted to map 1 byte here to 1 byte here. And this was not very efficient, so we grouped those bytes together in 2 pages. And then what we do is we basically split the memory into these pages. Okay, and 1 page here might be mapped to 1 page here. And this can be an arbitrary mapping. Now the question that we had then was, how large would one of these pages be? How large is one of these pages? And we decided, based on the address, that there are some sizes that are nicer. Let's draw this pointer here again. Pointer. And this pointer now will be a lot larger because we're talking about a 64-bit pointer now. 64-bit pointer. A 64-bit pointer, we know that 1 hex character has 4 digits, 4 bits. 4-bit binary digits. So 1 hex character, that's 4 bits. Another 4 bits. Oh, maybe I want to use a different address. Let's again take a stack address like yesterday. So we take a stack address 7. Oh no, it's not 7 in 64-bit because think about it. Where would 7 go? 7 would be somewhere in this non-canonical space in the middle. So this space is actually very small. So either we start with a lot of zeros or a lot of Fs. As we said, we actually only have 48 bits. So let's start with the 48-bit address because this 48-bit address fits in this virtual address space. So I will write that here, 7, and then the rest is Fs. And I will write a 48-bit pointer here, 7FFF. Then we have another 4 Fs. This is now 4, 8, 12, 16. This is 32 bits. We need some more bits, F, F, F. Let's say we put an 8 here. Okay. This is almost correct because this is not yet 64 bits. And what the x86 architecture requires is that we put a sign extension up here. So that means that all these bits here, they will either be 0 or 1, depending on what the topmost bit here is. And this is a 0, so it's all zeros. And this is how we get to the non-canonical space. This is the, let's write a different address. This here, if I put an F here, this is the last address before the non-canonical area. If I go one step further, let's do that as well. I write down a second pointer. And in this pointer, I want to go for the first address after the non-canonical area. So I will just do +1 and see what happens. So 0, 0, 0, 0, 0, 0, 0, 0, because we did +1, 0, 0, 0, 8. Okay, let's also write down what this 8 means in binary. 1, 0, 0, 0. And that means, because of this size extension, that all these bits have to be 1. Sorry, and this is not correct. It's not 1, because a 1 in hexadecimal is not a 1 in binary, all 1s in binary representation. But these bits all have to be set to 1. So we would have something like this, and it's 16 times. So this is an F, and another F, and another F, and another F. There are no addresses, no virtual addresses between those two. Between those two, that's the non-canonical area. Because currently we only support 48 bits, and this is a clever way to have this future compatibility, that if we extend this at some point, we can just relax this constraint here a bit and not require the first 16 bits to be all the same bit as this one. But as we do this, we just skip this non-canonical area because we have to set all of these to 1. Okay, non-canonical addresses, yes, anything between those two. Okay, so we have two addresses here, and now we wanted to map them to pages. So this page here, let's draw this here. This would be a page, and we wanted to have a very simple management of the physical memory. Basically, we want to have 1 bit of information per physical page, just telling us whether or not this page is in use, which is a 1, or it's free, then it's a 0. And we have this information for all these pages here. So maybe some of them are in use and others are not. Each page, so you can also see that they are just one after another. So the page is always also page aligned. We will see in a second what that means. Let me write page here so that we also have that on the whiteboard. The page has a number of bits. It goes from 0 to 4095. We had this on the whiteboard as well yesterday. And the last 12 bits, this was a design decision, was this part here. Okay. These bits were the page table index. Oh, sorry. Actually, I should be a bit more careful because I now have 2 addresses here. Let's start with only the upper address. So I will remove the lower address so that we are not confused by too many addresses here at once. Okay. This is the offset. We call this the page offset. And this, in this case, FFF is 4095. This points to the last last byte of the page. So now we know where in the page we want to access a byte. Okay. What is the next step? The next step is that we needed these tables to map virtual addresses to these pages. And we will start with a single layer, just as we did yesterday. And we call this the page table. So it's a table where we find the pages. How large is the page table? Can you write that in the chat? So this is 4 kilobytes. And the question is, how large is this one? 1024, 1023 bytes, 4096. These are numbers, but I don't know what size they would be then. 1 kilobyte. 1 kilobyte. A page is 4 kilobyte. Why would a page table then be 1 kilobyte? So what is the design goal here? We want this to be very easy to manage. So when we need a new page table, we need to allocate space in the physical memory. So what would be a size that we can easily allocate in this bitmap, which splits the entire physical memory into 4 kilobyte blocks? The entire physical memory. There's one block size that would be very nice, and we choose exactly that for the page table. And it's not 4 megabytes, it's not 8 kilobytes, it's 4 kilobytes. 4 kilobytes of memory. 4 kilobytes of memory, exactly. This will be 4 kilobytes in size. Just the same as the page, because if they have the same size, I can use the same bitmap here to manage this. This will make it easier for me as the operating system developer to implement this. Okay, how many entries does this page table have? And for that, we need to think about how large does one entry have to be. And for that, we need to know what one entry stores. And the entry stores, we had that yesterday as well. This entry stores where the page starts. It stores the physical address of the page, basically. It's not entirely true. We don't need to store all the physical address bits of this page, because we know that it starts at one of these boundaries. So we know that the page starts at an offset where all the lowest 12 bits are 0. So we don't need to store them actually. In the chat, yes, correct, 8 bytes. We would need to store 8 bytes to store the full address because it's now a 64-bit address. That's correct. But 64 bits, we actually know it's just 48 bits, right? And we also know that the last 12 bits are not required because they are all 0. We know that. So we only need to store actually not a physical address here, but we will store something else. Let's maybe take a closer look into that. So I will take a look at one of these entries here. Okay. What is stored in such an entry? First of all, we store whether it's present or not. If it's present, 1 or 0. Oh, I can't read that in this case, but let me write that down again. It's 1 or it's 0. One of the two. Okay. What else do we need to store in there? We need to store whether it's writable, for instance. Write 1 or 0. What about other permissions? Is it a user page? User page, or is it a kernel page? We can also say 1 or 0. So we can set all the permissions there. And one very important value we need, and it's not the physical address, but we instead store something that we call the PPN, the physical page number. These pages all have numbers and they start with 0, 1, 2, 3, 4, 5, and so on. We just number these pages, and this is the same as storing the physical address, because this page here, the physical address would be null. This address here, the physical address would be null x1000. You see? This page here, the address would be null x2000. So you see that the address always, the address of the physical address of the page always has these last 3 digits, hex digits 0. We don't need to store them because we are page aligned. That means if we cut those last 3 digits away, let's do that. If we cut them away, then we actually have the physical page number. Let me write that down here for a second so that you can also note that the physical address and the PPN, how do they relate to each other? The physical page number equals the physical address divided by the page size. Sorry, I'm not used to handwriting. I have to correct this. Okay, page size. Okay, does that make sense? We have a physical address, we divide it by page size, and that's how we get to the page number. And that's the same for the virtual page number. We could do the same here because it's also just split up in the same way that we start at 1 here, and this is page 0, page 1, page 2, and so on. The virtual page number is the virtual address divided by the page size. So the relation between a page number and an address is always that it's divided by page size in the one direction, and in the other direction you have to multiply it by page size to reach the start of the page. Okay. And this is really nice because page size is 4 kilobytes, and that means we can truncate this a bit. And for this PPM, we only need 48 minus 12 bits, because 12 bits for the page offset, we have that here, offset 12. And that means we need to store 36 bits. Okay. If we have a newer architecture where we don't need 36 bits, where we don't have 48 bits, but maybe more, then this will be actually a lot more than 36 bit as well. So maybe to be future-proof, it also would make sense to design this to be extendable. Okay, 36 bits. How large is one entry in bytes? Oh, we actually need to store at least 39 because I drew those 3 bits there as well. 39 bits. How do we store 39 bits? In how many bytes? Before it was nice. We had 32 bits and we stored it in 4 bytes. But now 36 bits, 39 bits, maybe even more. Five bytes. Let's try this with 5 bytes. How often does 5 fit in 4096? So we can do that. 4096 divided by 5. Oh, this will not be nice. So we will have 1 left over, 1 empty byte left over. If we say it's modulo 5, then it's 1. This is not a nice number. Let's try the same with 6. Is 6 a better number? 6, then we have 2 bytes left over. Oof. 7, maybe 7? No, 7 will also not be nice. Okay, what do we do? And this is the point where I used to say we have to use actual numbers, right? Actual numbers like 1, 2, 4, 8. There are no actual numbers in between those. We can use only powers of 2. So we have to go to the next power of 2, and that means that one entry here has to be 8 bytes. We have to go to the next 64 bits. Even if we don't use them, we use 8-byte page table entries. That means how many entries can we have here? 8 bytes into 4 kilobytes. That fits, that goes from 0 to 511. Oh, this is a change from yesterday. That means we don't fit as many bits in there. We don't need that many bits to find the right entry. 512. That means we cut the next 9 bits off here. Okay, let me draw that here. So this is 1, 1, 1, 1. In this case, it's 1, 1, 1, 1. And one more bit from this F. Okay. And this is what we provide here to the page table as the page table index. And the page table index has 9 bits. Okay, great. So we also can now apply the next step, the same as we did in the lecture yesterday. What do we call the next level? We just copy paste our design here. And maybe this is also a good, yes, directory, page directory, right? A table and then it's a directory. Okay. And how many entries does this have? How large is this? And also we can at this point think about how much memory this page table is responsible for. 512 times 4 kilobytes, that's 2 megabytes. So now a page table, as opposed to the 32-bit case, is not responsible anymore for 4 megabytes of memory, but now it's responsible for 2 megabytes of memory because we use fewer bits for the page table. Okay. Oh yes, the page table is still 4 kilobytes, but the problem is that 4 kilobytes divided by 8 bytes is 512 entries, and we need 8 bytes per entry because we need 64 bits. This is the same as 64-bit. Okay. Okay, this is nice. So we introduced this page directory. The page directory, how many entries does it have? And how large is one entry in the page directory? Well, the page table lies in the physical memory as well. Right, let's say it's here. And we need to find this page table in the physical memory. So it's the same as the page table. Yes, it's exactly the same. We copy paste this design here to the next level and it's 511 again. We need the next 9 bits here. Okay, so that means we have 3 bits from this F. We have 4 bits from this F. And we need another 2 bits from this F. Oh, this is much uglier than yesterday. The design yesterday had such a nice split up here. But this is okay. Let's call it page directory index. Okay, this is the page directory index. We still have 2 bits left over here. 2 bits left over. Okay. How much memory do we manage with that? So let's go point here. How much memory do we manage with that? Well, the page table manages 2 megabytes because it's managing 512 4 kilobyte pages. 2 megabytes. Okay. The page directory 512 times 2 megabytes. So that means 1 gigabyte. One page directory is responsible for 1 gigabyte of virtual memory. But this is not enough. We need to get to 256 terabytes. Okay. What do we do? Any ideas? Well, Intel also at some point decided we need to extend this. And the first extension that they did was actually to 36 bits of physical address space, and that meant that they still had 32-bit addresses, but they had 36-bit physical addresses, and they went for this design so far. And then they said, well, we still have 2 bits left over. If you would take the case with 32 bits, you would have 2 bits left over. So what did Intel do? and this is called PAE mode, the physical address extension mode, they introduced a new and very, very small table with just 4 entries and called it the page directory pointer table. The page directory pointer table. And this would contain 4 different page directory pointers and would point you here. Okay, and this goes here. Yes, that's not very nice, but it can be extended, and this is what they did for the 64-bit case. So let's go for the 64-bit case that we are actually interested in. And in this case, we have a full another level here from 0, a lot of entries, 511. And now we need, again, 9 bits. Page library, I also like page library. Page directory pointer table is not so nice, especially then if you talk about the page directory pointer table entries. You need a lot of words to just say what you mean. So let's split up this address further. So we have we have 4 more bits here for this F. So it's 6. We need 3 more bits from this F. Okay. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, great. And then we call this the page directory pointer table index. Okay. Page directory pointer table index. Complicated name, right? And this goes, we provide this number here as the index, and this will tell us where the page directory starts. A page directory pointer table has 512 entries, so it's responsible for 512 page directories. And in terms of memory, this means it's responsible for 512 gigabytes of memory, because one page directory was responsible for 1 gigabyte, page table 2 megabyte, page 4 kilobyte, 4 kilobyte, 2 megabyte, 1 gigabyte, 512 gigabytes. It translates 512 gigabytes of virtual memory to physical memory. Okay, and let's see what we have here. We have left 1 bit from this F, and then 4 bits from this F, and another 4 bits from this hex character. This is nice. So we have exactly 9 bits left. What do we do with it? What do we do with it? Any ideas? We need to maybe create another table. Yes. And this one, oh, now we need to take care. So let me compute what this number actually is. This is not 511. This is 255. So this will go somewhere here in the middle. 255. 255. But of course, the table goes to 511. It starts at 0. So it's again a table like the others. But in this case, because of this address here, we are selecting a different index. Okay. Okay. Yes, I like this name proposal. Page directory pointer table pointer table. Yes. But Intel also realized at this point that, no, just screw it. We just call it page map level 4. Yeah, just doesn't matter anymore. Just level 4. If you take a look at how ARM called this, ARM called it page table level 0, level 1, level 2, level 3. Done. Quite boring, right? ARM is a boring architecture. But that can be a good thing. So how do we find the page map level 4 then? We still need to find this. So where do we get this address from? We get this from the CR3, absolutely correct. CR3 register contains the base address of our translation hierarchy. The page map level 4 has 512 entries. The page directory pointer table is responsible, each page directory pointer table is responsible responsible of 512 gigabytes of memory. So this is now 512 times 512 gigabytes. That means it's 256 terabytes. That's exactly the size of the virtual address space that we had. Perfect. So that means we can again think about this as the ruler from school, like yesterday, where we had these larger slices here. This is maybe the page map level 4. Right, and within the page map level 4, this is like this. The entire thing is the page map level 4 because the page map level 4 just splits these into blocks. So this is the first 512 gigabyte of our virtual address space, and they will go to one page directory pointer table. So this goes here. So if we have an address here, it would go maybe in the first entry here and in the second entry here, something like that. So you can just imagine this as like in school, this millimeter, centimeter rule. Just imagine it has more layers, like for meter and kilometer as well. Okay. Great. So this is how pointers in principle work. The present bit, each of these layers has this present bit. If we have a valid stack address, this present bit will always be set to 1. If the present bit is not set to 1, what happens? If I start accessing, I access an address here. I should add this as well. Page map level 4 index has again 9 bits. What happens if I access an address, go to this location, and here the present bit is not set in the page map level 4? What happens? A page fault, exactly. We get a page fault. And this is how addresses can be invalid, because some of these pages are not mapped, and that's why we get page faults, or as we called it in ESP or SAP, we get seg faults if it shouldn't be a valid address. For instance, for the null pointer, this present bit will not be set, and therefore we get a page fault. There are multiple comments in the chat already. This design looks, the performance will be bad, the overhead will be bad. Yes, we will also talk about performance later in this class, but for now, yes, this will perform a lot of memory accesses. For every single memory operation, we perform not just one memory access to this page, but also instead 1, 2, 3, 4 more memory accesses. So in total, we perform 5 memory accesses instead of 1 now. Yes, it looks expensive in terms of performance, but there are tricks how we can make this better again. In terms of overhead, this is actually quite nice. Let's assume we go for the minimal case again. We need a single page. Then we have an overhead of 4 kilobytes plus 4 kilobytes plus 4 kilobytes plus 4 kilobytes. That's an overhead of 16 kilobytes. That sounds a lot because it's factor 4, but actually it's very small. It's just 16 kilobytes. And as soon as I need multiple pages within this page table, this gets a lot better. And if I would have the full virtual address space, let's assume we could fill the full virtual address space. Then we have here 2 megabytes of memory mapped, and for that we have an overhead of 4 kilobytes. And we would have 512 of these page tables. For these, again, an overhead of 4 kilobytes. So for each layer, we have an overhead of 4 kilobytes divided by 2 megabytes. So that means we have an overhead of 1 divided by 512. A bit more because this is recursive, so you would have an overhead of 1 divided by 512 plus 1 divided by 512 to the power of 2, 1 divided by plus 1 divided by 512 divided 1 divided by 512 to the power of 3 and plus 1 divided by 512 to the power of 4. So the overhead is really, really small. The only thing that really that is the substantial part of the overhead is this one layer, and that means it's an overhead of 0.2% roughly, if you would map all the pages. 8 kilobyte pages. We don't use 8 kilobyte pages because that would be ugly. We would need to use one more bit here, so we are just using 4 kilobyte pages. There's no reason to switch to 8 kilobyte pages now. And also, so to 8 kilobyte pages, the iPhone switched to 16 kilobyte pages, but not to 8 kilobyte pages. Okay, let me hide the whiteboard for a second and check out the questions on the Menti, because there are quite a few questions. But as I said, during the lecture, it might make more sense to ask via the YouTube chat, because you will get a faster response there. No, the t-shirt is actually, it says zombie load, and if you type in zombie load into Google, I'm sure you will find a website. It was quite some media coverage I had. I actually gave an interview to the Deutsche Tagesschau on TV about this attack. How can we have negative value of gigabytes on the first slide? I didn't really get it. The question is, how do you compute the address? Of course, you can say, oh, I'm speaking about where in memory something is, and it can be at 0 gigabytes, or something can be at 1 gigabytes, or at 2 gigabytes, or at 3 gigabytes. But you also can start counting at the top and count from top to bottom, and then you would start counting at -0 gigabytes, -1 gigabyte, -2 gigabytes. So you're basically saying the end of the address space minus this many gigabytes. And this is the same because if you know integer arithmetics, this will just overflow. If you say -1 gigabyte, or if you say -2 gigabytes, and your address space is 4 gigabytes in size, you will end up at 2 gigabytes again. If you say in a 4 gigabyte address space -1 gigabyte, that's the same as 3 gigabytes, because it always just wraps around. It's a convenient way how to express where the kernel is, because it will be the same across different architectures with different pointer sizes. Why is the canonical in the middle of the memory? It's in the middle of the memory because I am showing this again. Because of this, because otherwise, if it wouldn't be at in the middle of the memory of the address space, you wouldn't be able to do this very cheap trick of just copying the bits here, just doing a bit extension, a sign extension, basically. And this is a very nice way to be future compatible. So that's why you put it in the middle. So you would use the first 16-bit to access the non-canonical area. If you set any, so if you would have an address, any address where these bits do not all have the same value, or where these bits do not have the same value as exactly this bit here, the topmost bit from the 48-bit address, then it would be a non-canonical address. That means in this middle area that we cannot access. Okay. Since those pages are aligned in physical memory, we will never use the lower part of PDPT and PML4, since RAM is always smaller than 128 gigabytes. No, this is not correct. So let me show you this one again. The page map level 4 splits up the virtual memory, and virtual memory you always have 48 power of 2 to the power of 48 byte virtual address space, no matter how much physical memory I have. So in SWEP you will boot a system with where each process has 256 terabytes of virtual address space, and the physical memory is 8 megabytes. Megabytes, not gigabytes, but megabytes. So the PDPT and the PML4, they split up the virtual address space, and here you would have in the virtual address space, you would have the user space in the lower address part from 0 to 128 terabytes, and in the upper part from 256 terabytes, from 128 terabytes to 256 terabytes, you would have the kernel. What does it mean when we have an overhead of 1 in 512? The overhead, well, for 1 byte, for 512 bytes of memory that we map, we have 1 byte of overhead. That's fine. That's an overhead of 0.2% approximately. What is the canonical and what the non-canonical? I missed that somehow. We will talk about that a bit more in the lecture. So we will continue a bit more on this topic in the lecture on Monday. And there we will also talk again about the canonical and non-canonical memory. The canonical memory is the part of memory that actually exists. So it's in the virtual address space. I have these 2 addresses here. Yeah, maybe let me write that down again, but I probably have to remove this anyway. So let's delete this one. We don't need it anymore. Okay. Okay. Let's do this again. So we have an address, and the address, the requirement is, because that's very easy to implement, and we currently, so what we want is, we want 64-bit pointers. But that's expensive. So that means people will be sad. What we do instead is use 48 bits and sign extend. That means that we actually don't support 64-bit pointers, but the top 16 bits. Let me hide this Menti for a second. The top 16 bits will have exactly the value of bit number 47. So the topmost bit of the 48-bit pointer. Okay, let's try to look at an example. So we have a 48-bit address. Let's take this address. I start with the null pointer 00000000. Then we have 0000, and we have 0000. So this is 16-bit, 32-bit, 48 bits. Here's 48 bits. This is the sign extension. These bits, these zeros, have the same value as the first bit of this 0. This is the lowest address that we have in our address space. Let's go for the highest address before the non-canonical gap, and that would be 7, because 7 is the highest number that we can have here that still has a 0, and then F, 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 F. This is the highest address before the non-canonical memory gap in the middle. Then there's a huge gap, and I can actually compute the size of this gap, because it's the size of the gap would be, size is 2 to the 64 minus 2 to the 48. This is not a lot, right? This is just, this is 2 to the 64. How much is that? And does anyone know the units larger than terabytes? I think it's then petabyte, and then we got after petabyte, because we are already at 60 here. Maybe someone can look that up, what comes after petabyte. I rarely use that large sizes. So this is something like exabyte, probably exabyte. Exabyte. So 4, this is 2 to the 4, so this is 16 exabytes minus 256 terabytes. Yeah, so this is approximately 16 exabytes because terabytes doesn't even fall into account. It doesn't matter. It's still approximately 16 exabytes, right? This is a really huge gap. That's the largest part of our address space. Okay. So this is a really huge gap here. Gap size, we computed this. It's approximately 16 exabytes. The distance between those two, we can also compute what the delta between those two is. That's 128 terabytes. So we have 128 terabytes of usable memory, then almost 16 exabytes of non-usable space. And then we continue with the first address that has a bit set here, but all the other bits set to 0 because that's the lowest number we can have here. That is after this gap. 0, 0, 0, 0, 0, 0, 0, and another 4 zeros. Okay. And we now need to sign extend, so that means we have to copy over this 1 bit here. And that means that this will be 1, 1, 1, 1. That's an F. And all the others will also be Fs because we have to copy this 1 bit over again. It's sign extended. Okay. Now, what is the largest address in our address space? Well, we know that it's all going to be all Fs here, but also all the other bits here will all be F. So that's F, F, F. That's the largest address in our address space. Okay. And this is again 128 terabytes. And these together, if we add them together, we get 256 terabytes. And that's exactly 2 to the 48. As I said, 48 bits. We are using 48 bits here. I hope that clarifies a bit the situation. So we are talking, I forgot some zeros. Of course, we should write down the zeros. 0, 0, 0, 0, because this is again sign extended. And this is also correctly sign extended because this one has the highest bit set. Okay. How do we know if the address is kernel space or non-canonical? Well, if it's non-canonical, it's somewhere in this address range in between. If it's in between this address space, you don't even need to access this address. You already know that it's a non-canonical address, but if the pointer value is between those. There cannot be a valid pointer between those two addresses. Okay. Whether it's a kernel address or not, that's maybe a bit more difficult to tell because that depends on this user bit in the page table entry. If the user bit is set to 1, it's a user address. If not, it's a kernel address. So anything that would place the kernel space somewhere in the address space, if you would say, it's at the upper half of the address space, that's just convention. That's just an implementation detail of maybe one operating system. Okay. Why does the virtual memory go up to 256 terabytes and not 128 terabytes? Because it's 48 bits, and that's 256 terabytes. What are the use of the rest 128 terabytes when the 128 terabytes is for user space and the last 2 gigabytes are for kernel? Are the remaining 128 terabytes just empty, or does it have some use? There is some use, so the kernel usually uses that, for instance, for the identity mapping. You would map all the memory that you have in your system, or even large parts of the physical address space, map there, and by that use this virtual address space. If the canonical space starts at the address, the canonical space starts at address 0 and it has a gap in the middle. The non-canonical space is in the middle. At what point starts the kernel? We already had that was minus 2 gigabytes, and that means that we have here another 4 Fs and here an 8. That's minus 2 gigabytes. Okay. What is the pointer at the bottom of the board? The address which has to be translated? Yes, the address that we are translating. How did we come to splitting with 9 bits? We made one design decision. The one design decision was the page size. The one design decision that we made was the page size. And the page size, we designed this to be 4 kilobytes. Everything else falls logically from that. Because now, if we take a look at the physical address space, the physical address space has to be split into these 4 kilobyte pages. That means that any table that we want to use also has to be 4 kilobytes. The pages are 4 kilobytes, page tables are 4 kilobytes, and any other layer is also 4 kilobytes. We cannot work in any other memory unit now. And that means that we have to figure out how many entries we can fit into 4 kilobytes. And the number of entries that we can fit into 4 kilobytes is 512, because we are working with 64-bit addresses. And 64-bit doesn't fit in 32 bits, so we can't use 4 bytes. We have to use 8 bytes to store them. And 4096, 4 kilobytes divided by 8 gives us 512. 2 to the power of 9 is exactly 512. That's the number of bits to be able to reach any offset in this table, to store an index that can reach any offset in that table. Okay. Is the offset always 12 bits? Was another question here that I already clicked away. The offset, it depends on your design. In our design, the offset is 12 bits. So the size of the page map level 4 in PPT is 512 gigabyte each. No. The size of the page map level 4 is 4 kilobytes, and also the size of any other layer in this page translation hierarchy. Any of these tables is exactly 4 kilobytes in size. And in the page map level 4, what does it mean if we have 255? It still goes to 512. Yes, because we were looking at an address which started with 7FF, and that means we have to go to this entry 255. Should we always take 12 bits as an offset and then consider the next 9 bits? It depends on the architecture. In our case, we made the design decision that we have 4 kilobyte pages. 4 kilobytes is 2 to the 12, so that means 12 bits. And then from that, it logically followed that we would also make the page tables the same size, 4 kilobytes. And because we are working with a 64-bit system, that means that we need 8 bytes for an entry. And that means that we can only fit 2 to the 9 entries, 512 entries into one page table. That's why we have this design with 12, 9, 9, 9, 9. When calculating the overhead, how do we come to the 2 megabytes? If you start with the most basic case, you have one page and you have a page table. Then the page will be 4 kilobytes and the page table will be 4 kilobytes. But in one page table, you can actually map 512 pages. So actually you can have 2 megabytes of useful data, of actual data, and the page table will still be just 4 kilobytes. So the overhead for 2 megabytes of memory is then 4 kilobytes of memory. So every process would store a pointer to the page map level 4. Yes, that is correct. Which will get into the CR3 register on a context switch. Yes, also correct. Where are the addresses to the other tables stored? In the page map level 4. We are always storing the address of the next layer in the layer above. And only the page map level 4 doesn't have a layer above. So we need to get this address from the CR3 register. If I want to access one bit in physical memory, we have to go through CR3, PML4, PDPT, PDPT page at a given offset. Yes. What happens when we run out of physical memory? Then we might not be able to map a page in the virtual memory anymore. So we can only run out of physical memory while changing these maps. So we are changing these maps, and while doing that, we could run out of physical memory. And in that case, we wouldn't be successful in mapping the page. Mm-hmm. Do you mean with 1 byte overhead that 1 byte gets lost? No, 1 byte is, so overhead means we use this for metadata. We store meta information about the page in these page tables. For instance, where the page is, the address of the page. We need to store this somewhere, and that is the overhead that we have. So the BIOS lies on almost the highest address because it lies at FFF. That's not entirely correct. So if you would take a look at the last lecture again, the BIOS actually boots in 32-bit mode, and there we have only the last 8 digits here because it's a 32-bit address, and this is the first instruction that is executed, yes, but it's not where the BIOS starts. The BIOS starts at a bit lower address. You could also see that in the in this address listing that I had on the slides in the last lecture. But where are all the these terabytes stored? How is this information stored? Well, this is virtual memory. This is virtual memory. We don't map all of this onto physical addresses. Most of these addresses will not be valid, so we don't need to store this. And this allows us to have concepts like invalid addresses. Before, we couldn't have invalid addresses because all addresses, any address we would access, would map to physical memory. Now we don't need to do this anymore, and we can have a lot of invalid addresses in our address space. And this allows us to debug programs. Why is it enough to just store the offset in each layer versus store the full 64-bit address? Because each page is page aligned. That means the last 12 bits are 0. If the last 12 bits are always 0, and I would give you if I would give you a piece of paper where I omit the last 12 bits, would you be able to write them down there? Yes, because you know they are always 0. And it's the same for the hardware. The hardware is able to compute from the page number the start of the page, because it's always 0. The last 12 bits are always 0 for a page start. If we want to map a physical address to a virtual address, usually, so maybe this is also something, usually we map a virtual address to a physical address. So because the mapping translates virtual to physical address, but okay. How do we do that then? In the other order? So I'm not sure what the question is referring to. Usually you can only translate virtual addresses to physical addresses. Translating physical addresses to virtual addresses is another topic, and that's you would have to create a data structure where you have this inverse mapping. But for now, we just care about the mapping from virtual to physical addresses. So only the page table level checks whether the page is for user or kernel. Could it be also possible to check it on other levels? No. On a page table level, you perform all these checks. You check whether the page is present, whether it exists, so whether this mapping is valid. You check whether it is a writable page or read-only. You check whether it is a user page or a kernel page. You check whether there are a set of more bits. You can actually look that up in SWEP. If you have the IDE open right now, just open the file pagingdefinitions.h, and there you will find a struct for each of these layers. And for instance, you will find the page table entry there. It's a struct, and you can see all the members of this page table entry in there. Could it be possible to check it on other levels, so the time to okay, so basically you want to say the bit, whether it's a kernel or a user page, you could use that on multiple layers. Yes, the first result, so if you go through this address translation, if the processor finds that in the page map level 4 it says any address in this region that this page map level 4 entry is responsible for is a kernel page, then the processor will not check any further. Yes. So the first information that it finds already matters. So if you start with it is user accessible, it is user accessible, it is user accessible, and then say it's a kernel page, then it's a kernel page. But if you start with it's a kernel page, then you can't go back from that. So it will then always be a kernel page. So as soon as you've seen a kernel page bit somewhere in this translation, it will be a kernel page. When having 4096 entries in a page table with each page 4 kilobytes, then we restrict the physical address space to be 4096 times 4 kilobytes. I don't know what design would... So if you would design it like this, each page is 4 kilobytes, then it depends on the pointer size, how many entries... Okay, so I think what you are referring to is you would then need a very small pointer size. So with a pointer size of 1 byte, so that's 8-bit, you would be able to do that. And if you have 4 kilobytes plus 8 bits, that would be 8 plus 12, so it would be 2 to the 20, and that means that you could handle 1 megabyte of memory. If you have 1 byte of physical page number and 12 bytes of 1 byte of physical page number and 12 bits of offset. But this is this is not the design that we drew on the whiteboard, so not the design that we talked about. How do we know if a physical page is free? Because the operating system, so you, maintain a bitmap where you store for every physical page, is it free or not? And if you say, oh, I need a physical page, then you just flip this bit in this bitmap, and now it's your physical page that you can hand to someone. Do we have a table, or do we need to search all processes page tables? Oh yeah, we do have a bitmap. We definitely have a bitmap. We don't want to search for through all processes page tables. Does every segment have its own virtual memory mapping, CL3, PL4, and so on to page? Segmentation is a separate concept. So you have segmentation and you have virtual memory with paging. They don't interact with each other that directly. So you would have, for instance, segmentation that translates your address first into another address, and then this address is provided as a virtual address to the page translation. So they happen independent of each other. Where is the transform look-aside buffer? We will talk about the translation look-aside buffer, but not today. All the tables are still stored in physical memory. Yes, that's correct. Then let's go here. Can you explain the overhead again? I don't really get the meaning of it, or probably missed it. So the overhead, you need to store these tables somewhere. You store them in physical memory. And the question is, how much physical memory is occupied when I have a process that works with a certain amount of memory? Let's assume we have a process that works with 2 megabytes of memory. Then it needs 2 megabytes in pages. That is 512 pages. This can fit in one page table, and that means that the overhead to work with 2 megabytes of memory is one page table, which has to additionally be placed in the physical memory. And that means that you have in the memory not 2 megabytes of data that you actually want to work with, but 2 megabytes and 4 kilobytes. So the overhead is 4 kilobytes divided by 2 megabytes. Maybe I can find another explanation. let's assume so overhead. There are also real-world examples where you have overheads. For instance, maybe you want to buy beer for a party, and then the question is, how much beer do you buy? You know that the location where the party is, there is someone who also will drink a few beers because he's organizing the location, and he's there, and you have to take that into account because he's also drinking a few beers. And basically this, of course, this person will not drink 1 beer per guest, right? But this person will only drink a fixed amount of beers. Let's say the person drinks 4 beers, and every guest also drinks 4 beers. And if this location can fit 512 people, you can compute how many beers you need to buy, right? You don't just need to buy 512 times 4 beers, as many as you would have for the party, but you additionally have to buy these 4 more beers for the host. And that's the overhead, 4 beers extra for every 512 times 4 beers that you actually want to serve to your guests. It's just a simple overhead computation. There's another question in YouTube. Okay, there's a lot of questions in YouTube. Since the top 16 bits need to be 0, we can know whether it's user space or non-canonical or kernel space. And I thought maybe we can differentiate between kernel and non-canonical with topmost bits too. Well, non-canonical addresses have the top. If you take a look at the top 17 bits, you can always say whether it's a non-canonical address. Whether it's a non-canonical address or whether it's a canonical address. You can always say that. The other part, whether it's a kernel address or a non-canonical address, I don't see why why you would need this distinction somewhere, because you don't just generate non-canonical addresses. You don't just it's not like you would need this distinction anywhere. But if you take a look at an address, the top 17 bits will tell you whether it's a non-canonical address or not, because the top 17 bits need to have all the same value. They are either all 0 or they are all 1. If not, it's a non-canonical address. If they have the same value, all 0 or all 1, then they are a canonical address that can be valid, and it can be a kernel address or a user space address, and we cannot distinguish just by looking at the value whether it's a 1 or a 0, whether it's a kernel or a user space address, because a kernel page could also be in the lower half where the bits are 0, and the user space page could also be in the upper half where all the bits are 1. It's possible, so we cannot just generically, based on the address, say this. When we have a process and we implement virtual memory, if we do a dereference on a virtual address, who and at what time exactly interferes and translates this virtual address to this physical address? So we configure these translation tables that we had on the whiteboard. We configure them as the operating system. But the hardware, the processor, will do that internally for every single memory access. The processor will walk through these tables and translate the virtual address to the physical address according to our configuration. So we configure it, the CPU very, very quickly does the lookup and gives us the physical address. So in the future, when we have more physical memory, we will need a PML4 that takes the first 16 bits, right? Yes, to this part. No to this part, because 16 bits is really not nice. 16 bits, that would require a page map level 5 of a size of 2 to the 16 times 8 bytes. That's not a nice size. That's 2 to the 6 is 64, and 10, 64K, and then 8 bytes. That's 512 kilobytes. That's not a nice size for a table. So probably not 16 bits. But if you have a better suggestion for how large the PML5 should be, better than 16 bits, then please write it in the chat or in the Menti. So what we just saw was only a hardware implementation. It is the hardware implementation that you are all using. It's x86 64. It's the one that SWEP uses. That's why we looked at this, because we want to prepare you for the assignment. So every process has its own mapping that is stored and changed via the CR3 register. The CR3 register just stores the base address, the address where the page map level 4 is. We change the mapping by actually changing these tables in memory. They are stored in memory. We just change these values in memory. Can two processes store, for instance, malloced data on the same page, despite when using shared memory? They shouldn't. If they would, I would consider this probably a bug, because it's not possible without shared memory for two processes to work on the same page. If they can work on the same physical page, then this is shared memory. They can, of course, work on the same virtual page, but this translates to a different physical page, and then they are not actually working on the same page. So each process has only one PML4 table. Yes, absolutely correct. How large is our physical address space in our design? In our design, the physical address space is maybe 48 bits, but it could also have a different size. 52 bits would also be fine. We don't really care about the size. It has to be less than 64 bits. 64 bits is the upper limit for the physical address space, and until this size, our design would still work in the same way. How can we use 256 terabytes of virtual memory if we only have 8 gigabytes of physical memory? Where do we store this 256 terabytes? And if we can store only 8 gigabytes of virtual memory in physical memory, why do we need 256 terabytes? Well, to, for instance, have an address space where you can have gaps. Here you have a stack and there you have a stack, but in between there's a large gap so that we don't introduce any bugs and don't run from one stack into the other. So this is one feature. We can have a sparse address space. The other part is that you can also map memory multiple times. If you take a look at the processes running on your system, you will find that they have significantly more virtual memory allocated than you actually have physical memory in your system. Because they will map memory multiple times, you can have thousands of processes that use the same shared library that is a few megabytes in size, and they don't need a few thousand times these few megabytes, because they can just use shared memory for that. But because they are separate processes, they will need virtual memory mappings for these shared memory mappings. They don't consume physical memory or just the overhead, so just a small amount, but it allows us to have separate address spaces per process. So I need to have a process with 128 terabytes virtual address space. It should have 256 terabytes of virtual address space, okay? But let's continue. Now each process has at least one thread which is part of this 128 terabyte address space. The thread can access this and has its own stack only. The stack of the thread will be part of the address space of this process. Any thread can access any stack. It's part of this address space. It's just one of the pages in there, or multiple of the pages in there. The stack of the thread is part of the address space of the process. It's part of the address space of the process. Page map level 5, maybe again 9-bit. Yes, I like this design. This is exactly what you would do. And then you would have 57-bit of the virtual addresses, meaning that you can cover, instead of 256 terabytes of virtual memory, you then can handle 128 petabyte of memory. And this is an extension that is already implemented in the first CPUs, because we need it in the cloud, where you handle large amounts of data. Probably we'd have, yes. And another table with the remaining 7 bits, or maybe we won't use the remaining 7 bits anytime soon, because having 128 petabyte of memory is a lot. Can you show how 2 processes translate the same virtual address to different physical addresses? Yeah, in principle I can, but so I think we have to move the rest of the assignment presentation to Monday, because I'm still on slide 8 out of 150, because there were a lot of questions, and of course we can do that, but we will continue on Monday then with the presentation of the assignment. Okay, let's do this translation for 2 addresses, 2 processes. So you would have 2 processes, and they have their own virtual memory of process 1 and process 2 virtual memory. Okay, and you have one address maybe here in the lower half. This is a stack address, and this is a stack address, and let's write this address here. Okay, these are the same addresses, and this address is I will only do the 32-bit variant now because it requires less space, so let's do the 32-bit variant, but it works the same in 64-bit. So I will take a stack address CFF, that's the offset, and then we have F, and another 2 Fs, right? This is 1, 2, 3, 4, 5, 6, 7, 8. This is a 32-bit address. This one is split up. So we have the page table index here, and we have the page directory index here. We have the CR3 register up here for this one. Process 1 has its own register set, and the CR3 register defines this address space. Okay. And process 2 also has its own CR3 register value. When it's scheduled, the value of this CR3 register that we stored somewhere in the kernel will be loaded into the CR3 register. So what happens then? The CR3 register tells us in both cases where the page map level 4 is, or in this case we are in 32-bit mode, so the page directory, and we have 1023, 1024 entries in there, and here we have a different page directory. Okay. Actually I wanted to put a 7 here because it's a stack address. Okay, so this first entry here is 200, and it's 511. Okay, so this is 1023, this is 0. We have here the entry 511, 511. Let's draw the physical memory also here. Maybe this is not good because you can't see it. So maybe let's draw it. Can I draw it here maybe? The physical memory. Okay, physical. Okay, this page directory, let's say this page directory is here. PD of process 1. And here we have another page. This is the page directory of process 2. Okay, so you can see that this is actually here, and this is here. Let's say this has the address or the page number 1, and this is the page number 0, 0, 1, 2, 3, 4. So we know that the CR3 here has the value 4, and here it has the value 1. So we get to different page directories, and they have different values in there. Now we take the page directory index, we pass it onto here and here. And now we will take a look at these entries. So in this case, the present bit, maybe it's a present page, it's a stack page, so present is 1. It's a user page, sure, it's 1. It's writable, right, it's 1. And the physical page number of the page table, let's write that properly down here. And I will also, I will also remove these dashed lines because they are later on confusing, but I just wanted to illustrate you how they are placed in the physical memory. Okay, so present 1, user 1, write 1. And then we have here the page table ppn. This is exactly like that in the code. If you take a look at, go and open this file if you have an IDE at hand right now. Open the paging definitions.h and scroll down down to the page table entry struct. There you will find exactly these members. Maybe they are named a bit differently, but present is named the same way. PT, ppn is named the same way. So these are basically the members of this struct. And the PT ppn here will have a value. Maybe it's okay. Maybe we have here the page table of process 1, and maybe we have here the page table of process 2. Okay. So this will point, and of course they will have multiple of these page tables, right? There will be many of these page tables, but this is a very small example. So the page table ppn for this process number 1 will be 0, 1, 2, 3, 4, 5. Okay, so it's 5, and this points us then to this page table here. Page table from 0 to 1023. Okay, and you can see that this goes to different physical addresses because it already started with different physical addresses. And then maybe we have here the page for process 1, and here the page for process 2. Okay, 0, 1023. The page table index goes here, and also it goes here, right? Because we're translating the same address in 2 different processes. And this will now return different values again for the 2 processes because it's stack pages. So here we have present is 1. I've written this a bit too far on this slide. Present is 1. Okay. User is 1. Writable is 1. And the page, so let's write that down fully. So the page ppn, physical page number in this case is 0122. And this will point us to a page. Okay, this is how we find page 2. And here we have the same. We have present equals 1. We have user it's 1. Writable is 1. And the page ppn is, in this case, 0123. Okay, this is page number 3. So this will be a different page. Let's draw it here. Page. Okay, and it points us there. This is how translation works with 2 processes which access the same address, a stack address, but they are in separate address spaces. They have different values for CR3, and from that they go through an entirely separate hierarchy of translation tables. Okay, let me clear this up again and go back to the questions. Okay, where's the phone? Here's the phone. Okay. Yes, I've shown that, so this is done. So if every process has its own virtual memory, does every user process have access to the kernel memory at -2 GB in virtual memory? Yes, it doesn't actually have access, but the kernel is there. So if you switch into the kernel for a system call, then the kernel is exactly accessible there. And it is also there, if it's not accessible, it's still there in user space at -2 GB in virtual memory. What is the technical difference between a physical page which is shared and one which is not shared? The technical difference is that in the last step that I've just shown you, they would go to the same page PPN. That's a shared page. Same page PPN in two different hierarchies. Can we please end at 4 p.m.? We need to take, we take too long every lecture. Yes, the thing is that I also want to answer the questions. So if you ask fewer questions, I will also stop earlier. But I didn't take into account that we have 40 minutes of questions. So of course it's fine if you ask questions, but I mean, today I was able, I wanted to present assignment 1 to you, and I was able to cover 8 out of 150 slides. So yeah, finishing on time is always possible if there are no questions, but to me it's more important that if you have questions, you ask them and I answer them. Okay, does a process only receive a long list of pages or sometimes even a complete page table if it requires huge amounts of memory? I'm not sure what this question refers to. So this design that we drew there, every process has to work with that design. More RAM, PML4 or PML5, PML6, etc. So more RAM, more tables. Well, the physical address space is not the same as the RAM, right? Because we have things in the physical address space. We've seen that in lecture 2. That there are things in the physical address space that are not RAM. And that's actually the larger part of the physical address space that is not RAM. And so there might be other reasons why we need more virtual address space. So it's not necessarily true that we need more layers then. Actually, the amount of RAM is not coupled to this, but the virtual address space. If we need more virtual address space, then we need more tables, more layers, not if we have more RAM. For more RAM, we could also just increase the entry size and have larger physical addresses, and we would also be able to cover then the larger physical address space. The questions today cleared up a lot of misunderstandings for me. Yes, that's why we have them here, and that's why I also take the time to answer them. So that page table entry in SWAP defines all the bits of the address in the page table. It defines all the properties of the page table, of the page, sorry. So if you map one page, this entry would define all the properties of that 4 kilobyte page. Yes. Okay, and there is a last question. Could you explain the identity mapping again? So I think we've seen often enough already the how the mapping works in principle, but I will instead take a shortcut here and just draw it like this. So we have the virtual address space here, and there's a region here which starts, in the case of SWAP, it starts at F 0, 0, 0, 0, 0, 0, 0, and that's another 4 0, 0, 0, 0. This is where this address starts, and it goes from here to there. It's 1 terabyte or 1 gigabyte maybe. I think it's 1 gigabyte only. 1 gigabyte. And any address in here, if we take a look at the physical address, physical memory now, this is physical, this is virtual. This will be divided into pages, right? So these pages here will map exactly, so this is 0, this is 2 to the 48, and this is 0, and this is also maybe 2 to the 48. And now this will map to the first page here, and the next one maps to the second page here, and this one maps to the next page here, and this one maps to the next page here. So it's just a one-to-one mapping. You would be able to tell me if I would take a look at this first entry here. Let's take a look at this entry. Let's try it here. Present bit. Is it present? Yes, it's present because we are able to access it. Then let's take a look at the user bit. Is it user accessible? No, because if the user could access this, the user could access any physical memory location. That cannot be allowed. Is it writable? Yes, it's writable for the kernel. And then we want to know what is the physical page number. The physical page number for this first page here is 0 because it maps the first page in the physical memory. Let's take a look at the second page here. Second page, ppn is 1. Yeah, because it just maps one page from here to one page here, one page here, one page here. This allows us to access physical memory because, as we said, the kernel also works on virtual addresses and has no way to access physical addresses, except if we introduce a mapping like this, where you just have to add this offset to the physical address, and then you are able to access this as a virtual address. Okay. So let's continue. And this doesn't consume any memory because this is just a mapping to the physical memory, but this memory is not consumed. You wouldn't mark these pages as used because you just want a way to access these pages that are in use. Is the overhead why some of the RAM is not usable? For example, when I buy 8 gigabytes of RAM, it's usually 7.6 gigabytes. There are various reasons for that. I don't think you would see this like that in the operating system. The operating system would count the memory consumption for the page tables as part of the memory consumption of a process. If the kernel is at -2 gigabytes, does that mean that every process has a kernel memory in the virtual memory, even if it is a user process? Yes, otherwise you couldn't context switch into the kernel. As you remember, in the beginning of this lecture, I said the context switch from user to kernel only changes this execution mode. It keeps the same CR3 register. It keeps the same page map level 4. So the page map level 4 has to work for the thread, whether it's in user space or in kernel space, in both situations. What dot size variable for in page? Okay. In the page table entry, you will have a dot size member, all right? And you can set it to 1 or to 0. There's a feature that I haven't shown you today, but I will show that to you on Monday or Tuesday, depending on how fast we are, where you can take a shortcut in this translation. So you basically don't translate always to a 4 kilobyte page, but instead you can set the size variable in a page directory, for instance. And if you set it in the page directory, then you mean that this page directory entry directly will map to a 2 megabyte page and not to a page table organizing this 2 megabyte region, but instead you will directly map to a 2 megabyte page, and the semantics then change a bit because of course for a 2 megabyte page you have a different page size, you have a different number of address bits, so all of this changes a bit, but we will cover that in a later lecture, not today. We still have 15 minutes, so we can still start to talk a bit about the assignment, but not as much as I would have liked to. So let's just start a bit with that. Processes and threads. So currently we have the situation with the user process that there's a scheduler. The scheduler schedules thread. They are the schedulable base unit. And some of these threads have kernel registers and user registers, but some of them don't. And actually only those threads that are user processes have user registers. And the user process also has a loader, it has an arch memory which controls the virtual memory, and it has, in the arch memory, there's a member variable for the PML4 that we've just seen on the whiteboard. It's there in the as a member variable in this class. You can take a look. And this CR3 register is also stored here in the user and kernel registers, and you get it via user process loader arch memory and get the member page map level 4 there. Threads are the schedulable base unit. Please don't change this. Don't schedule processes, because processes don't split up the execution times. Processes split all the other resources. The thread status currently can be running or sleeping if it's waiting for some lock, or to be destroyed if the thread should be destroyed, because it cannot destroy itself. It cannot execute its own destructor. Is this enough? Well, the question is, what about the syscall sleep? Maybe we have to come up with an idea there. User threads must be derived from thread. So you will create a new class, for instance, something like user thread that must be derived from thread, and user process must not be derived from thread anymore. So you will have to change this design, and it's a good idea to just start with that. Remove that inheritance there and try to get it back to work where the thread is then a member variable of the user process and not the user process derived from the thread. How do you create a user process in SWAP? I think you've all done that in the tutorials, but I have this here for completeness. And the next part is already about how to start threads in SWAP. And to do that, we run into a problem a bit, because this is again connected to this context switching topic that we had a few lectures earlier, I think on Wednesday. And now we have the problem that we want to switch into a thread that has never been scheduled before. And to understand how that works, we need to understand how function calls work. And the old variant would be the cdecl function calling convention, but we will actually take a look at the system v function call ABI. So we will look at function calls in 64-bit mode. I've written a very small example here. So we have this example with main and then ABC 7, 14, 0, and then we call a function add A and B, add A and B. It adds A and B. Okay, writes that in C, returns C. I've compiled this program, okay. Okay, let's take a look at this. So we start here with push RBP. This is the function prologue. We store the base pointer on the stack. Then you can see this here, sort on a stack now. And then we set the RBP to be the current value of RSP. That's where the new stack frame starts. Then we make some room for variables, 32 bytes in this case, for local variables. Then we place the local variables on the stack. Because they are local variables, they have to be placed on the stack. And that's it. Now, in the next step, we want to perform a function call. And a function call in 64-bit mode works like this. We move our arguments into registers, and the function call calling convention defines which registers we use for that. The first argument goes into RSI and the second argument into RDI. I often mix these two up, the order, so it always makes sense to look up whether it's correct or not. So in this case, we move first the value into a register so that we can work with it. We move the other value, the second function argument, also into a register. Then we move this second argument into RSI and the first argument into RDI. And then we call this function add, and then add will generate the function prologue again. So we update RBP and RSP. We move the value from RDI into a local variable, and we move the value from RSI into a local variable. And then we move them from these local variable locations on the stack back into registers, okay, into RDX and RAX. We add those two with the add instruction, and then we have the result in RAX. You can see this here. Then we can clean up the stack again. We pop the base pointer from the stack. Now the base pointer is pointing up there again. And then we use the return instruction to go back to this function that we pushed, the return address that we pushed on the stack while using the call instruction. While doing that, we pop this from the stack, so the RSP changes. We then place our result into a local variable. Then we place our result from local variable into RAX, because the calling convention says that return values are passed in RAX. The leave function again resets the RSP, and with return we can return to the calling function. So this is how function calls work. And why is this relevant for us? Well, the part that we've already looked at are system calls, and there we place these values into registers. But for pthread functions, we also have to know how to place values in the registers there, because the thread function, as you know, takes as argument a void pointer. And maybe there are even more arguments that we need to pass to these user space functions, and we need to know how we pass these arguments to functions. For syscalls with interrupt 80 and in kernel, you can go for the syscall exception. But for pthreads, we really need to know this calling convention. Let me quickly check one question here on Menti. Should we delete member variables in thread H? Is that advisable? I would move them somewhere else. You can move around variables as you like, but some of the member variables make sense in the thread class because they can be convenient to access. For instance, I would keep the loader there, although all the kernel threads don't have a loader. It still is convenient to have that. Process synchronization is also important, and you will have to implement that. Processes and threads, they share memory, they share other resources, and without locking, they will be destroyed. And for that, I've prepared another Menti, because yesterday students asked to have more of these pro-contra slides. So we can do another brainstorming, and then we will end pretty soon after this one. After this slide. The term critical section. Why is it a good or a bad term? I want to know why this is good or bad. Someone is saying it's not descriptive. Not descriptive. Is there anything positive about this term? Critical section? Someone says it's misleading. Okay. Not descriptive. Misleading. Still a place in code. Okay, so this would speak for critical section because it's a section in code. Confusing. Needs locking. So the thing is, I think critical section is a very good term if you want to talk to someone on a very high level, because everyone knows this term. The problem with this term is that it's not very descriptive. It's actually quite misleading, because we always, when talking about a critical section, we actually want to talk about resources and protecting resources. So a lock, also a locking mechanism, always refers to a resource. Can we just disable interrupts? Not really. This is not an option, because if we just disable interrupts, what if another thread already was working on this resource? So that would mean we would have to disable interrupts every time we access this resource, and this is not really feasible. The synchronization mechanisms that we can use are these: spin locks, mutexes, semaphores, and condition variables. And on Monday, we will continue here, and we will talk about how to construct all of these, and we will have code for that on the slides. I would like to, as requested, end on time, but that means that we have to shift this presentation of assignment 1 to next week. Would that be a problem for anyone? Let me check. Does anyone have the design, the student debate before the lecture on Monday? If so, we would probably have to continue and continue with the explanations, because you need the knowledge then. So let me check the timeline maybe. I probably have to check the schedule for that. So do we have groups on Monday before the lecture? The lecture on Monday is at... Okay, let me check. Lecture on Monday is at 2 p.m. Yeah, so the lecture is at 2 p.m. So that means that we only need to check whether there's any tutorial on Monday before 2 p.m. But at the same time, it's also on Monday, that would already be unfortunate, because then you have to prepare everything. Okay, do we have any tutorials on Monday? We don't have any tutorial groups on Monday. That's great. Then let's continue with this presentation of assignment 1 on Monday. Someone also is saying they are not next week. Okay, yeah. If they are not next week, then we have enough time anyways. That's good. Then we can stop here, and I will just check whether there are more questions, and then we can stop here. Okay. So someone is saying, please continue. We'll continue on Monday. That's soon enough. Is the kernel already multi-thread? Yes, it is. I would like to work during the weekend on it. You can, it's no problem. What I recommended already earlier this week is split up user process and user thread. This is something that you can already do. Make the thread constructor then reachable from a syscall. So you have a syscall, and the syscall calls the thread constructor, then you have a new thread. Then make a second syscall, and these are different tasks for different people in your team. So splitting up thread and process, that's probably a task for 2 people to look at together. Exposing the thread constructor to a syscall, that's another task. Exposing the copy or creating a copy constructor for a process, that's another task, big task. And this then also has to be exposed to a syscall. So you can already start working on that, and you will see, if you just try it, you will get farther than you would think. Student debates start they start on 15th of March, apparently. Yeah. So next week there's another tutorial, I guess, on virtual memory. So, yes. Thank you for the patience with the questions. By the way, it does not matter how long the lecture is because of the recording. I think for some people it matters because they want to participate live, which I also really like. Why is 1400? In my calendar it says 1400. Is it wrong? Let me check this timeline again. But no, it says yeah, probably I was in the wrong week here. Yes, it says 1800. It's at 6 p.m. on Monday. You're right, absolutely. We want the cat. I don't think the cat is here. Is it here? Yeah. Yeah. Yeah, I don't know whether she's coming here. Here's the cat. I see. Okay. Now we got this as well, and we are at the end of the lecture, and I would like to thank you for your attention and see you next Monday, on Monday. Bye.